Okay, 3.1, 3.2, this is going to be a brief lesson because when we talk about derivatives in Chapter 2, I've talked about the applications of derivatives. So in explaining why we're taking derivatives of things, I've often mentioned the fact that in a position time graph, the first derivative is the instantaneous rate of change between meters and seconds, right? So if we're talking about a position time graph where we have meters up here, and then we have seconds over here, and this is the path of the trajectory of some object, or so the height above ground over time, or the distance away from starting point over time. Then if we take a derivative at any point, right, or this slope of the tangent line at any point would be the instantaneous change in y, or meters, over the change in x, or seconds. So the slope, right, the slope of a tangent is instantaneous meters per second. And I've got that, I guess, written down here. So position time graph, first derivative is the instantaneous velocity of the particle. The slope, or the derivative, at that point is in the units meters per second. So consider this. Consider another graph where we have a velocity versus time graph. So this is now meters per second per second. So we are at a certain, velocity. So let's say we start off at 0, and the velocity increases over time and then stays steady. This is a steady velocity over time, and then this object goes down to 0 meters per second. Well, if we take a look at a tangent line at a velocity versus time graph, that is how the velocity is changing over time. So velocity changing. So if you have meters per second, that's the same as meters per second squared. And that is what? The second derivative then, or the derivative of the derivative function, is the second derivative. So the first derivative is velocity, the second is acceleration. Thank you. So this is the application, and we've talked about this before. If it's the first time you're hearing this, then you've missed something. But this is what's important for 3.1.3.2. Now it's all about application for 3.1.3.2. We're not going to talk about the rest of Chapter 3 for now. We're going to come back to parts of it. But most of Chapter 3 would be the applications of derivatives in other sciences, physical sciences, social sciences, business, that sort of thing, biology, that sort of. So feel free to look through Chapter 3. We aren't going to study all of the different applications, just because of time for one, and that sort of thing. But please feel free to look through Chapter 3 and look at what else the derivative and the second derivative can tell us about other applications. But you want to remember here that the first derivative for position time is velocity, and the second derivative is acceleration. And that's what we're going to primarily deal with in these sections. Okay? Any questions there? Okay, let's take a look at a position time graph, okay, meters, seconds, that looks something like this, okay? What happens if this looks something like this? So my question to you is, what does it mean when sections of the graph are concave up, that is where the curvature, right, over time is kind of up like this, okay, or parts of a parabola that would be opening upward, or concave down, that is parts of the graph have a curvature like this where it's part of a parabola that would open down. So if you think about that, right, what's happening here is, and there's a couple tangent lines drawn here, okay, there's tangent 1, and the next second, this is tangent 2, let's say, the third second, this is tangent 3. So what's happening to the slopes of these lines? Well, they're going from this to this to this. So they are increasing, aren't they? 1, 2, 3, and so on. So if you look carefully, on a concave up, the velocity is always increasing. The instantaneous rate of change is always going up and up when the concave is up. So that's important. That's important. So concave up, velocity is increasing. All right. Now, what about concave down? Is it the opposite for concave down? Well, If you have concave down, let's say you start with a velocity that looks like this over this interval, what's happening to the velocities? Instantaneous velocities are coming down. So we've got this going to this, going to this, going to this, right? So on concave down, the velocity, which is represented by the instantaneous rate of change of the slope of the tangent line to a position time graph, the velocity is decreasing. Now, how would you interpret a section of time where your velocity is increasing? If you're driving a car and every second your velocity is greater than it was the second before, what can you say that that vehicle is doing? It is what?
Speeding up.
It's speeding up. What's another name for speeding up? It's accelerating positively. It's got a positive acceleration. Okay? So think about this. When velocity is increasing, acceleration is positive. Okay? If, and I got to think about how you guys see this. Okay, so if the velocity is increasing by the same amount every unit of time, that's a consistent acceleration. You see that? And if velocity is changing very quickly and then changing very slowly, then the acceleration is changing. You have a high acceleration, then a lower acceleration. And if the change in velocity, it remains constant, then acceleration is what? 0. If the velocity decreases over time, this is now negative acceleration. You're slowing down. That's a negative acceleration. So, very important to note, this is positive acceleration. Or in this, from 0 here to a positive acceleration means that the second derivative of x is greater than 0. What is acceleration? It's second derivative. So the second derivative is always greater than 0 over this interval. Even though velocity is positive, remember, velocity is positive from here, well, through the whole thing, actually. Right? Because there is no point where the tangent line is a negative slope. So this is always positive here. So velocity is always positive. This object is going in the same direction the whole time. It's just speeding up and slowing down. Speeding up and slowing down, staying the same velocity. Okay? So in this section then, when it's concave down, okay, that's negative value of acceleration, or f double prime of x is less than 0. On a straight part of this curve, okay, the first derivative is positive. It's this line, the slope of this line, right? But there's no concavity. It's not positive or negative, right? It's like 0 concavity. So f double prime of x is 0 here. From C to D, if that line is straight line. Now, I haven't talked much about the first derivatives, okay, so I'll talk about that in a second, but let me just erase this. I think we're understanding this. So can we talk about first derivative here from 0 to a?
Yeah.
Okay, what is the, what is it here? It is what? What can you say about first derivative?
Equals 0.
The first derivative equals 0? Well, remember, the first derivative is where the tangent line is 0. Okay, where the tangent line is 0. So all of the tangent lines are positive here. So it's positive here. Now, even if the acceleration is less than 0, here as well, f prime of x, and I'll use the same notation, it's also greater than 0, because all the slopes are positive. Remember I said that the velocity here is actually positive the whole entire time. So don't get fooled that velocity, so velocity can be positive. Oh my, what did I just do? Velocity can be positive while acceleration is negative. All right, so velocity here is 0. All right. Now, I should make mention here, endpoints, okay? You cannot take the derivative of an endpoint. So the derivative does not exist here at this point. You can't say, oh, look at it, levels out right here. The function has to be continuous, so the left limit and the right limit must agree. If there's no function over here, we don't know what the right limit is. So just as a note, I'm not sure if I've mentioned this or talked much about this yet. I should have probably. But, oh yeah, maybe I did. But I don't know if I talked about endpoints of a graph. So remember when I said a function is not differentiable at a cusp or a corner or at a jump discontinuity, etc.? Remember that? So I should have mentioned too, I don't know if I did, but I should have mentioned that at the end point of a graph, if there is a start and end point, it's differentiable all the way along here, but not at the very end. So you can't just say, oh, it just teeters on, this is the end point here, this is the... No, you don't know where it is because you don't have any function guiding you on the other side. So it's a function is not differentiable at its end points. So let's just make a note there. Because this would be the only possible place that you might think that the derivative is 0, see? This is slightly positive, that's still slightly positive. At e, we cannot take the derivative, technically. All right, so that was a little aside, but that's important to know. Okay, as we move on. All right, if s is 12 plus 30t, 12 plus 30t, what kind of function is this? Hoon, hi, wake up. What kind of function is this?
Linear.
Thank you, linear. We've got a y-intercept of 12, and we've got a slope of 30. Okay, so it's going to be quite steep, but it's going to be linear. You're right. Now, the first derivative. Now, the derivative is an expression for the instantaneous rate of change at any value of x. Well, what is the rate of change over this entire interval?
The glass cell, please call 205.
30?
Yeah, the slope of all the tangent lines are 30 because it's a straight line. So the first derivative should be 30. And is it?
Yes.
0 plus 30. It is. Okay, so hopefully that makes sense. If this was squared now, well, maybe we have something like, I don't know what that's going to look like here. 30t squared, something like this. Yes? Right? Okay? So if that's the case, squared, then the velocity, the instantaneous velocity is definitely changing. All of these slopes, right, are changing. So then this would be 12 plus 60t. I'm sorry, the derivative, 0 plus 60t. So it's going to be actually 60 times whatever the x value you choose. It's going to differ. It's going to be different, which makes sense, right? So let's get rid of that again. Let's get rid of this again. And yes, okay. 30. What is the second derivative?
0.
It is 0, right. Now let's see if that makes sense. The velocity is staying constant the whole time, so we're neither accelerating nor decelerating. So acceleration is 0. So, we good? Okay. So here's an example with the squared. I did that already. Let's just take a quick look. I want you to take a look through your textbook at these sections, 3.1, 3.2. Let's take a moment and we'll just conclude our lesson here in a second. Let me know if there's anything that, an example or something in there that you don't think that I've talked about for 3.1 and 3.2. If we just look at the textbook here, example number 1, let's just say. These are the types of questions you're going to be able to answer here now. If a stone is dropped from a cliff that's 122.5 meters high, and its height in meters per second is given by this equation right here until it hits the ground, find the velocity after 1 second and 2 seconds. Well, that's easy. We find the first derivative. Plug in 1, find an answer. Boom. Plug in 2, get your answer. Boom. That's going to be over here on the next page. What did I just do? Okay. Right? So plug in 2 into the first derivative. There's your answer, the speed. When will the stone hit the ground? Well, the stone will hit the ground when the height is 0. Right? So here's the height function. Let that equal 0. Solve for t. Boom. Done. No calculus there. Right? That's just algebra. What is the velocity when the stone hits the ground? Well, you have the time now. You found the time. So first derivative, plug in the value of the time when it hits the ground, you can find the velocity. All right? Now, in your physics class, you guys have been asking me about physics, okay? Physics applications, gravitational acceleration is negative 4.9 t squared. That's how it's 9.8 meters per second, right? So on an equation, you'd probably have the height that you drop it from minus 4.9 t squared. This is going to be a common part probably of your physics equations for falling objects, okay? This is tied to gravitational acceleration, which I think maybe is part of this question, I'm not sure. The second derivative would be the acceleration of the particle. And notice, the second derivative of this height function, right? The first derivative is negative 9.8 t. The second derivative is negative 9.8. That's gravitational acceleration. 9.8 meters per second in the negative direction down towards Earth. So that's your gravitational acceleration. Okay, so you could, again, when is the particle at rest? That is velocity 0. When is the particle moving in a positive direction? Okay, well, in a positive direction. Okay, so a positive direction, let's see, C, that's when the velocity is greater than 0. Now, when you find your velocity function, you set that greater than or equal to 0, solve for your t values. Do you remember how to do that? Remember doing sign analysis there? We're doing sign analysis? Nobody remembers sign analysis? I think we reviewed that at the beginning. Okay, well, let's take a look at 3.2. We might have to go there. Not SOHCAHTOA, no. Sign analysis. Sign analysis. Later. Okay. All right, so instantaneous rate of growth. What else? Population of bacteria. Oh, applications to chemistry. Okay, rate of reaction, instantaneous rate products or reactants to products. Whatever that rate of reaction could change over time, and so on. If you're given a function, you can find all that. So, oh, what's that? Wait. Was that 3.3? Did I skip too far ahead? Sorry. Wanted to stop at 3.2. Oh yeah. Rates of change in the natural sciences. Well, that's good for you to know as well. Okay. All right, so here's your assignment for 3.1 and 3.2 coming up right here. 3.1, 3.2, write it down, get started. Awesome.